All right, so we're going to do a couple more of these difference of squares, but this one, it's not to the second power. These are just higher degree pieces. So let me put the formula down here. It says when you're subtracting two perfect squares, 81 is a perfect square, and this is a perfect square. All right, that's the same as x squared squared. It's kind of weird to think of it that way. But when you have a difference of squares, it can be factored as such. You just square root that one to get a, and you square root that one to get b, and then one's plus, one's minus, okay? So for x to the fourth minus 81 here, you have to think about what times itself will give you 81. Well, that's 9, of course. And what times itself will give you x to the fourth? So what can you multiply by itself to get x to the fourth? Well, that's x squared. One's plus, and 1 is minus. I actually didn't realize that I had one like this in here. This one's actually kind of special because this will factor again. All right, this is the sum of squares here, so you can't factor that, and quote unquote, you can't factor it, but this one you can. I'm going to go ahead and do that. So I'm going to rewrite the first one, x squared plus 9. And then this is going to factor by difference of squares a second time. It's going to be x plus 3 and x minus 3. Okay, that was like, I think that was in our first video too. So that's the factored form of this. Okay. So we took the square root of x to the fourth, and that was the x squared. Square root of 81 was the 9. Okay. Here we're going to have what times itself will give you x to the sixth. That's going to be x to the third. Remember, you add the exponents. And then what times itself will give you 4y squared? That's going to be a 2y. And the other's a minus 2y. Okay, yep, that works out. And this one does not factor like this one did up here. This one was kind of special because it had another square and another perfect square. Doesn't always happen though. Let's look at the third one here. So square root of this, or what times itself will give you x to the 12th. That's going to be x to the 6th. One's plus, one's minus. And then what times itself will give you 16 y to the 4th? Well, that's going to be a 4 y to the 2nd and 4 y to the 2nd. Yeah, I didn't even notice I had these going on. This will actually factor again. This one will, right here. All right, so I'm going to rewrite this one. X to the 6th plus 4y squared. So this one won't factor again because it's the sum, but this one will. Okay. Square root of x to the 6th is x to the 3rd. Let's see here. I'll write it out like that. And square root of 4y to the 2nd, or what times itself will give you that, is a 2y. Then one's plus, one's minus. Cool. Yeah, I didn't even know I had those going on. Good. Last one here. So what times itself will give you this? That is 3y to the 4th power. 3y to the 4th. And then what times itself will give you 4y to the 10th is a 2y to the 5th. 2y to the 5th. And then one's plus, one's minus. And this one won't factor any further. I mean, 3 is not a perfect square, 2 is not a perfect square. Yeah, there's nothing times itself that'll give you y to the 5th. I mean, not unless you go to like fractions and decimals and stuff. So again, another way that they'll commonly rewrite this stuff, they'll be weird, but instead of 9y to the 8th, they'll rewrite it so that it's 3y to the 4th to the 2nd, because this and this are equivalent. They are the same thing. And then they would write 2y to the 5th, 5th to the 2nd. And then this one is equal to 4y to the 10th. And hopefully you can see how, or it's kind of weird. I know it's weird, but that's my pieces there and there, there, and there. Okay, if you wanted to check your answer, you could just plug in some number for y and go from there. All right, it works like that too.